We've done extremely well with speakers on cosmology, particularly from the Stag group at Southampton over this year. And our speaker tonight is an expert on astrophysical sources of gravitational waves. He's a member of the Gravity group in the Department of Mathematical Sciences at the University of Southampton. He's also a member of the LIGO Scientific Collaboration, the group that in February 2016 announced the first ever detection of gravitational waves, confirming an outstanding prediction of Einstein's theory of relativity and giving us the most direct view yet of those most mysterious of objects, black holes. Please welcome Professor Ian Jones.
So, I was able to walk here today. I live somewhere near the Port Flood Arms. I've given talks for many years all over the place, but I've never quite given one so close to home, I think. And I'm going to talk about all sorts of big numbers and all sorts of small numbers today, but I'm going to be talking about measuring distances in megaparsecs. I don't know what the distance is between here and my home in megaparsecs, but it's a very small number indeed. It's what I'm trying to say in a very roundabout way. It really is a pleasure to be invited here to talk to you today. So, I'm going to talk to you about gravitational wave astronomy. This story goes back a long way, but to begin with, let's just cast our minds back a few years. So back in February 2016, we made the announcement of the first ever detection of gravitational waves. And this funny little graphic that you can see here, that squiggle on it, represents a ripple in the gravitational field. These were the gravitational waves that we saw. So what I'm basically going to try and do now is unpack this, tell you what a gravitational wave is, and tell you why it was a big deal. And it was it created a lot of excitement at the time. I actually kept quite a few of the newspapers that came out just after it for posterity. And I've got images of quite a few. So this is the one from the Independent. So if anyone has forgotten what a front page looked like pre-Brexit, it looks something like this. So there's some sort of image there of sort of two black holes going around one another. That's part of the story. The headline is Theory of Relativity Proved. That's not quite a kosher headline. You never really prove stuff in science, right? Occasionally you get to disprove things, but nevertheless, you can see it was given the whole of the front page there. It was similar with the other newspapers. So what I'm going to try and do is explain what are gravitational waves, and why was this detection such a big deal. And to really tell you this story, I need to go back much, much further in time. And really, the story starts with Einstein himself. So back in 1915, Einstein published his theory of general relativity. This is his theory of space and time that explained gravity. And it was a very mysterious theory, and it didn't think of gravity as a force. It thought of it as this weird sort of curvature in space-time. I'm not going to plug that aspect too much. One of the main things for us is this, that in Einstein's theory of relativity, according to the theory, nothing can go faster than the speed of light. So that was something that he realized 10 years before in his special theory of relativity, but that was true also in his general theory of relativity. And that has two important consequences for what I'm going to talk about today. And the first is it leads, in a fairly natural way, to the idea of a black hole. So what is that idea? The idea is you've got some sort of body, and maybe it can emit light. But if there's some sort of limit, some sort of universal speed limit on how things can escape, then you can kind of plausibly see that if you make an object dense enough, if you cram enough mass into a small enough space, then, because of this universal speed limit, nothing can escape, not even light. So that's a kind of a hand-waving description, but if you really look at Einstein's theory, you do indeed find that that's the case. If you squash things enough, if you were to shrink our sun down enough, you get a black hole. So that image that you can see on the left there, that of course is an artist's image of a black hole. The idea is that the black hole's in a binary system, so there's another star right next to it. That's the big thing that you can see on the right. And gas is coming off the big star, and it's swirling down, and it's forming that disk, the so-called accretion disk around the black hole. As that gas swirls and falls down onto the black hole, it gets compressed, it gets hotter and hotter, and it starts glowing and producing X-rays. And that image that you can see on the right, so that's a real astronomical image, and you can see a tiny little point labelled there called Cygnus X1. This was seen back in the 1960s, and people realised early on this is an excellent candidate for a black hole because no one could think of what else could be, what other sort of object other than a black hole could be producing such a strong gravitational field that it could squash gas and heat it up in that way. That's sort of indirect evidence that black holes exist. And then we had a second piece of evidence that Einstein's idea was right about black holes. This is actually a video, so let me play it. So this is a video that shows the motion of stars at the centre of our galaxy. Each of these little dots is a star that goes around it. What you can see is that they're following trajectories that reach some point indicated by that star in the middle, and they zoom around. And yet, when you look at that point, it doesn't seem there's an awful lot there. What astronomers have figured out is that the centre of our galaxy and the thing that these stars are orbiting around has got a mass of about 4 million solar masses. And yet it's a very, very small object. So again, it's a sort of a plausibility argument. We can't think of anything else that could, other than a black hole that could be sitting there and causing all those stars to swirl around. And so, for some time we had this sort of circumstantial evidence that black holes exist and are real. Then the second consequence of this universal speed limit, this idea that nothing can travel faster than the speed of light, is to do with the gravitational field itself. So everything produces gravity, we think. Even me now, standing here, if I wave my arms around, my mass is moving, so the gravitational field that I produce is changing. And yet Einstein says that nothing can go faster than the speed of light. So what's happening to the gravitational field outside of me? Well, what Einstein did was he looked at the equations of his theory back in 1916, and he realised that changes in the gravitational field themselves are subject to this speed limit. And these are the little ripples, these are the gravitational waves. So the idea is when gravitational fields change, you get little ripples that go out in the gravitational field itself. So that's what gravitational waves are, the little ripples in the gravitational field. And pretty well, any motion of mass produces gravitational waves. As I say, me moving my arms around produces them. Guess you can't feel them, right? They're a bit weak. It turns out if you put the numbers in, and if you really look at the theory, the strongest gravitational waves arriving here at Earth will come from violent astronomical events, because they're the ones, those are the things with the biggest masses and the biggest speeds, and these are the things that produce the strongest gravitational fields. So, for instance, if you look at the top left here, if you had two stars in a binary, so one star orbiting another, because those stars are moving around the whole time, the gravitational field is changing, that produces gravitational waves. And that's the type of source of gravitational waves that I'm going to talk about for most of this talk again. That's the thing that we've seen. And in principle, though, there are lots of other interesting things that we think go on in the universe that could produce detectable gravitational waves. So we know that when stars get old, many of them explode, supernova explosions. Those explosions can produce gravitational waves. At the bottom left, we know that there are lots of very small, dense stars in our galaxy that we call pulsars that spin around. If they're not perfectly axisymmetric, if they've got some sort of bump on them, some little mountain, then as they spin, their gravitational field will change. They'll produce gravitational waves. And then finally, that image at the bottom right that you can see, that's not a gravitational wave image, that's an image of the electromagnetic spectrum of some light that was left over after the Big Bang itself. That's the cosmic microwave background, some sort of glow. It gives us a snapshot of what the universe was like when it was about 380,000 years old. We would love to see what gravitational waves were produced early on in the universe and get the gravitational wave analog of that electromagnetic picture. That picture, as I said, it's basically a snapshot of the universe when it was 380,000 years old. The gravitational waves that would be left over from the early universe, they would tell us about the state of the universe when it was some fraction of a second old. So in principle, could see much, much further back, much closer to the Big Bang, if we could only see this sort of gravitational wave background. So in principle, we could learn an awful lot through looking at gravitational waves. Now, just as for years we had some sort of indirect evidence that black holes exist, we had some indirect evidence that gravitational waves exist, and that's what's shown on this plot here. So let me explain it. So on the horizontal axis, it's time. It's running from about 1975 to the year 2005. And the thing that's plotted on the vertical axis is some timing parameter of just one of these binary star systems. It's a system that consists of two very dense stars, two neutron stars, orbiting one another. On one of them, we see it's a pulsar, so we see it's a little sort of spinning lighthouse of light. So we get radio pulsations from it. And what it's meant is that astronomers over decades have been able to study in detail and with extreme precision the exact timing and the orbital period of this binary. And what's basically happening, what this picture shows, is that as time goes by, these two stars are gradually getting ever so slightly closer together, just by a very small amount, but it's the thing that's illustrated with these little black data points that you can see in the figure. And that curve that you can see wonderfully goes through those data points. That's what you get if you apply Einstein's theory of relativity to the system. So what's going on is that as these two stars orbit one another, they're doing just what I said. They're producing gravitational waves. Those gravitational waves, they carry energy away. The energy's got to come from somewhere. So it comes from the energy of the system, and it's that that's causing them to gradually spiral in. So if you take Einstein's theory and you try and apply it to the system, you get this lovely smooth curve that goes wonderfully through these data points. So in fact, these sort of measurements won the astronomers Holson Taylor the 1993 Nobel Prize. So this gave us some good degree of confidence that Einstein was on the right lines when he said these little ripples in the gravitational field, they exist, they're real, and they carry energy away from their source. So that was great, but both in the case of these observations of black holes using light, and these the effect of gravitational waves on this binary system, they're rather indirect. What people realized should be possible is to go one step better and actually directly detect gravitational waves. And this is the thing that was pioneered by this chap that's shown in this picture here. So he was called Joseph Weber, and back in the 1960s, he had an idea for how we might directly detect gravitational waves. You can see him standing in front of a huge bar of aluminium. It's about 1 meter long, very big, very heavy, and the idea is this. So what gravitational waves do when they travel through something is they make it oscillate ever so slightly. So I made that flippant remark, you can't feel my gravitational waves. Well, you can't because they're weak, but what they're doing, the gravitational waves that are going through this room all the time, they're causing everything in it to oscillate ever so slightly. And so the idea that Joseph Weber had was if he could take a metal bar and if he could somehow get rid of all the sort of random seismic noise, all the shaking from the ground, or at least get rid of most of it, then if his metal bar suddenly started shaking around, that could be evidence that a gravitational wave had passed through it. So that's what he did. He built this experiment, and in the 1960s, it was a big excitement. He claimed to have made detections. In fact, he claimed to quite frequently make detections. But other people didn't agree. So, of course, as soon as he announced his results, other people started building their own versions of his experiment. They simply didn't see what he saw. To his dying day, he kept claiming that he made detections, but it soon became clear to the mainstream that he just wasn't doing his statistics properly, and he hadn't really seen anything. Now, one of the limitations, and one of the reasons why we now know, looking back, it would have been virtually impossible for Joseph Weber to have seen something, is that his experiment was pretty small. So his metal bar was about 1 meter long. If he could have made a bar that was 2 meters long, then the amount of shaking that a gravitational wave would cause would be twice as big. If he could have had a metal bar that was 10 meters long, you'd be looking at 10 times as big an effect. So the point is, the bigger your experiment, the easier it is, because the more it shakes around. Okay, it's what's called a tidal effect. Now, there are practical limitations to how big you can build one of these metal bars. And so what people realized in the 1980s was that you needed to rethink completely how you go looking for these signals. And this is where the so-called LIGO experiment comes in. So LIGO, it's an acronym, the Laser Interferometer Gravitational Wave Observatory. There are 2 LIGO detectors in America, and there's one called Virgo in Italy. Well, I'll say more about all the different detectors in a while. And they're basically L shapes. So what you can see is basically an aerial image of one of these detectors. You can see one arm of the L extending up away from you and another arm extending to the left. And there's a little laboratory there. Each arm of this detector is 4 kilometers long. And the way the experiment works is that, so if I just move over here briefly, in this corner station over here, there's a very powerful laser. That laser light is split into half of the light goes along one arm, half of the light goes along another arm. There are mirrors at the ends of the arms, the light bounces back, and you recombine those 2 beams. And the way in which those 2 beams recombine, and whether or not you say get constructive or deconstructive interference between the light, depends on how far they've travelled. So what happens then if a gravitational wave comes along is it shakes this whole experiment around a bit. It might make one arm a little bit longer at a given moment, the other arm a little bit shorter. That's the sort of shaking that gravitational waves produce. And that shows up as some time-varying way in which the laser beams recombine then. And the point is, these laser beams, you can make this experiment really big, it's 4 kilometers long, because these laser beams are just traveling up and down vacuum tubes, up and down empty tubes. So it's not so expensive, it's not so crazy to build a really big experiment. I mean, ideally you'd make it even bigger than 4 kilometers, but even here, there were cost limitations. But what it means in practice is that this experiment, like a 4,000-fold head start on Joseph Weber's experiments. And to give you some idea of how delicate these experiments had to be to detect gravitational waves, this 4 kilometer detector is sensitive to length changes of about 10 to the minus 15 meters. So 10 to the minus 15 is 1 divided by then 1 and then 15 zeros. It is a fantastically small number. This is why, looking back, we don't think Joseph Weber could have done it with what he got. He wasn't sensitive to that smaller length change. You really needed a big experiment to do this. So there are 2 detectors like that. There's one at the top northwestern corner of the United States in Washington State. There's another one in the southeast in Florida. And as I said, there's another very similar one called Virgo in Italy. So these detectors started taking data around about the year 2002. They took data for a year, 1 year, 1 year. They saw nothing. Someone once described it as the most expensive empty data set in the history of science, which maybe it was at the time. So they kept taking data up until about the year 2010. We saw nothing. We kept publishing papers setting upper limits. Upper limits, what you say when you've not seen anything, right? You say, well, not seen anything, but we know that the gravitational waves, if they're out there, are no stronger than this level. But of course, that wasn't what we really wanted to do. So in 2010, we shut the detectors down, worked on them for about 5 years, and then came back with new and better detectors. And within about a day, 2 days, switching on the new detectors, this happened. So what's going on here, so this is the first ever detection of gravitational waves. If you look at that top plot, that's the signal that was seen in one of the 2 American detectors. We haven't got a laser pointer, or any sort of pointer. It's not the end of the world if we haven't. Right.
Probably not right now, this second.
That's okay. Oh, it's not a problem. So what you can see at the top left is the output of one of these detectors, the one in Washington State. And to begin with, it just looks like a load of scruffy noise. So time is running along the horizontal axis. There's about a third of a second shown in these plots. And it's the output of the gravitational wave detector on the vertical axis. And what the signal is doing, thank you, what the signal is doing is it's starting off very small, low amplitude and low frequency. You can't really see it by early times, but as time goes by you can pick out a signal that's getting bigger in amplitude, and it's also getting higher in frequency, and then it kind of sort of shuts off. And there's a very similar signal that was seen at the same time at the Livingston detector. Actually, it wasn't at the same time. It was, I think it was about 0.7 milliseconds different, but that corresponds to the light travel time of the gravitational wave between the detectors. If it had been at exactly the same time, that would have been a bit funny, but not impossible. So what this plot does is it time shifts one signal with respect to the other, and you can see that they match up quite well. And not only do they match up with one another quite well, the point is this. We've got Einstein's theory of relativity. Its equations are complex, but you can solve them on a computer. And if you solve them on a computer, it's precisely this sort of signal that you predict you should get if you've got two black holes in one of these binary systems. And unlike the Hulse-Taylor thing that I showed you before, so that, if you work it out, those two stars are going to inspiral and collide in, 400 million years or something. This is the last 0.3 seconds of one of these binary systems, just as the two stars have got so close that they actually coalesce and end up forming one bigger black hole. So what you can do is you can accurately solve Einstein's equations on a computer. It took people decades to figure out how to do it, but they did it. And it's precisely this sort of waveform that you get. People call it a chirp. I'm not going to embarrass myself by whistling or singing it, but it's like a bird's chirp in that it starts off at low frequency, and then its frequency increases and its amplitude increases, and it shuts off. It's a chirp, okay? And you can, in detail, extract information about what this binary system was, what the black holes were like, from looking at the exact shape of that signal there. And so there was then a very rapid effort to write this up and publish a paper. This is the abstract from the paper. I wouldn't normally show an abstract in a public talk, but there are a few amusing things to pick out from this. So this is the paper, Observation of Gravitational Waves from a Binary Black Hole Merger. So it's the paper that we've been waiting decades to write. If you look at the first author, well, if you look at the authors, it's B.P. Abbott et al. So the first three letters of the first author are A.B.B. So the authors are listed in alphabetical order. You can take a guess as to how many people are in the LIGO-Virgo collaboration, given that the first three letters are A.B.B. In fact, since then, someone joined whose name was Abadi. So poor old Abbott got displaced to second in the author list. And then someone joined whose name was Arsi, A-A-S-I. So they were the first role. But anyway, those two have left now. We're back with Abbott. So this Abbott's incredibly famous because he's the first author on. So my point is, it was a very big collaboration because there were people working on the detectors themselves in terms of the hardware. There were people doing the data analysis and the output, and there were some people doing the calculations as to what the signal should look like. So it was a big affair. So let me just pick out some of the numbers here. So the peak gravitational wave strain was 10 to the minus 21. What on earth does that mean? What this is saying is that when this gravitational wave came through our detector, it did just what we thought it would do. It made it shake around, but the fractional length change, sort of percentage length change, but in dimensionless terms, was 1 part in 10 to the 21. So 1 divided by 1 followed by 21 zeros. That's how small the effect was that we finally needed to detect to see these signals. Okay, Webber couldn't have done that. This signal had a false alarm rate of 1 event every 200,000 years. So these detectors are noisy because we can't completely get rid of all the random seismic noise and bits are shaking around. And so when you have an apparatus like that, there's always some small chance that just random noise in your two detectors will somehow conspire to give you something that looks like a signal. So in order for us to stick our necks out and submit this paper in the first place, we had to wait until we were confident that this was probably a real event. And well, this is saying that you'd only get something by chance like this once in a very, very long period of time. We had to have statistical confidence that it was a real thing. And as I say, the exact shape of that signal contains a lot of rich information as to what was going on. So we were able to figure out that this source was at a distance of 410 megaparsecs. So not in our galaxy, wouldn't expect it to be in our galaxy, it was in some relatively distant galaxy. And we're able to figure out what the masses of the two black holes were. So one had a mass 36 times the mass of our sun, The other had a mass of 29 times the mass of our Sun. So these are the masses of the two stars that collided. They ended up forming one single black hole, and the mass of that black hole was 62 solar masses. So you might be wondering at this point, astronomers can't add up and subtract numbers. 36 plus 29 minus 62 is 3. There's a missing mass that somehow disappeared from the system of 3 solar masses. That is not an error. That is the energy that so you could have, Einstein's equation E equals mc squared. There's like an equivalence between mass and energy. The energy equivalent of 3 times the mass of our Sun was radiated away in this 0.3 or so seconds. By that measure, it's one of the most luminous events that we've ever seen. It's not luminous in the normal sense because it's not light, but nevertheless a huge amount of energy in a tiny, some small fraction of a second was being radiated out. And even that just produced this tiny, tiny little wiggle in our detectors. So that was it. That was nice. So why was it, a big deal? Why was even the media excited about it? Well, there are 2 things to be said. So first of all, it was a big deal in terms of the fundamental science. It was the first ever direct detection of gravitational waves. Einstein had predicted them back in 2016. It was nice to, announce their detection exactly 100 years later in 2016. And it was the first ever strong field test of general relativity. People had done many experiments. It gave us confidence that Einstein's theory of general relativity, his theory of gravity, was correct. But there are always things like solar system tests or situations where the gravitational field was quite weak. What we've got here is 2 black holes smashing into one another and forming one black hole. This is as strong as gravity could get. So whereas we'd sort of done tests that were just sort of probing the weak regime of gravity before, this was going the whole hog and really, sort of nailing it and seeing gravity in its most dynamic, turbulent regime. And we shouldn't ignore, this gave us most direct evidence so far that black holes really exist and have the properties predicted by general relativity. Because as I say, this waveform, this chirp, it wasn't any old sort of chirp. It made sense in terms of Einstein's theory. But then the title of my talk was Gravitational Wave Astronomy, and the point is we're not just testing basic theory here, it's giving us a new way of learning about the universe. We've used light, well, we've used light for millennia to learn about the universe. This is enabling us to use gravity itself to do astronomy, hence the term gravitational wave astronomy. So for decades, when we're asking the government for money, we say, we are going to open a new window on the universe. So we finally got to say, we have opened a new window on the universe. It's a new way of seeing what's out there. We would never have seen these 2 black holes collide without a gravitational wave detector, because it didn't produce any light. So it's the first ever observation of a binary black hole system, and it's led to interesting questions. People are trying to figure out, how did these 2 black holes end up orbiting one another? How did they form a binary system in the first place? Jury's still out on that, but it's an interesting issue. So then in the next year, the Nobel Prize for Physics went to this. The 3 of the people that were instrumental in it, Ray Weiss, who did had a lot of the early ideas about the experiment, Barry Barish, who was one of the people that led the LIGO collaboration, and Kip Thorne was one of the leading theorists that used Einstein's theory of relativity to try and figure out just what gravitational waves would be like. Incidentally, a Scottish guy, Ron Draven, may well have been in line for the share of this Nobel Prize, but sadly he died just before, just too soon, so he missed out. But there's a long history of gravitational wave research in this country. So that was the detection of 2 black holes. But the story goes on, and what has happened a little more recently, back in 2017, is that we've seen gravitational waves from a different sort of binary system. This is a computer simulation of it, and the big difference here is that these 2 things aren't black holes, they're 2 neutron stars, they're 2 very, very dense stars. It's something like the mass of a sun compacted in like a 10-kilometer radius, and what's happened is they've come in and they've smashed together, and because they're stars, because they're made of matter, most of black holes, you'd expect an almighty explosion, and that's what that computer simulation is showing you here. And so this is something that, using gravitational waves, we wanted to see from the beginning, because we might expect, if we could detect gravitational waves from one of these events, there might be some almighty electromagnetic bang that would go with it. And so we were very interested in seeing if we could detect anything like that. And sure enough, it happened. So all of these gravitational wave events are labelled with dates. So it was the 2017, August the 17th. This bottom plot is showing the so-called time-frequency plot of the gravitational wave. My colour is showing its strength. So this is showing that over a course of about 10 seconds, the gravitational wave frequency went from about 50 hertz to 400 hertz. It's another one of these chirping-like signals. But the key thing here was, these upper plots, these are the output from some satellites that detect gamma rays. And for decades, astronomers have been seeing things called gamma ray bursts, bright flashes of gamma rays, and no one was entirely sure what they were. But one of the leading theories were that these represented two stars, two neutron stars, two very dense stars, smashing together. Well, this is from the gravitational waves. This is when the two stars collided, and about 1.7 seconds later, there was a big flash of gamma rays. So this was a big deal. This was the first time that we'd seen gravitational waves from something where there was an accompanying big burst of radiation, of electromagnetic radiation, because we were dealing with fluid stars. And so what happened then was, just like half the telescopes on the planet suddenly started pointing at one little bit of sky. It was supposed to be secret, and yet everyone knew that everyone was looking at something, so it didn't stay secret for very long. And what happened was, so this is designed to inspire shock and awe, this plot. The point is, not only was this seen in the gamma rays, that's what this little point is depicted there, very soon afterwards it was seen in the optical. This is an image of a galaxy here, and you see that tiny little dot there? That dot wasn't there the previous time astronomers had looked at this galaxy. This glowing dot had suddenly appeared, and this, we think, represents these two stars smashing together and leaving behind a very, very bright, very hot remnant. But then after that, it was seen in, this glowing dot was seen in the infrared, it was seen in the ultraviolet, it was then later seen in the radio, it was seen up and down the electromagnetic spectrum. So this is what people call multi-messenger astronomy, because we're combining gravitational wave detections and electromagnetic detections, and this created a lot of excitement, because there are things that you can do with this sort of thing when you've got two real stars, two neutron stars smashing together, that you can't do with two black holes, because you've got all this extra information that's coming from normal telescopes, from X-ray telescopes, from optical telescopes, whatever. And so this was a very exciting time. The media picked up on this one as well. Let me just give you a flavour of the sorts of things that you can do with this kind of system that you can't do if you've just got two black holes smashing into one another. One of the things that you can do is talk about how stiff neutron star matter is. So these neutron stars that smash together, they're even denser than atomic nuclei. They're incredibly dense. And we would love to know how matter behaves at these high densities. We can't, in our laboratories, even in particle colliders like so, we can't reach these very high densities. We would love to learn about how stiff neutron star matter is. Well, if matter was really stiff, these neutron stars would have been big, and as they got close to one another, you'd get tidal effects. One star would distort and change the shape of the other, and we didn't see any clear sign of that, so we knew that matter wasn't too stiff. So in other words, we could learn something about matter at very high densities from these. Another thing that we could do was do some cosmology. We could see, we could use the gravitational waves to work out what redshift this is. Don't worry if you know exactly what that means, but we can also measure the distance. The point is you can work out the value of something, one of the parameters that cosmologists care about, the Hubble constant, from looking at this, precisely because we can measure the distance from gravitational waves, and we can measure something else, the redshift, from the fact that we know from our optical telescopes where this was. We could place constraints on the speed of gravity versus light. Einstein said that these gravitational waves travel at the same speed as light. It was a prediction, it could have been wrong. Well, these two signals, they didn't arrive at exactly the same, but at nearly the same time. There's a 1.7 second delay, but we think that's probably just to do with the time it takes to produce the electromagnetic signal. So we regard that as a pretty good consistency test, that the speeds of gravity and light the same to about 1 part in 10 to the 15. And then finally, and this is the thing, that at the expense of everything else the media liked, there had been a puzzle for some time as to where the very heaviest elements, like gold, come from in the universe. We know that lots of the heavy elements, like carbon and oxygen, they're made in stars, and when stars go explode in supernova, these heavy elements are ejected out into the cosmos. But when people did the detailed calculations, they didn't think you'd get much gold and other really heavy stuff, the heavier elements, in these sort of stellar explosions. Well, because when two neutron stars crash together, you've got higher energies involved, they're very favourable sites for producing these heavy elements. So if you've got any gold on them, there was just a chance that it was produced when two neutron stars collided in time immemorial. So that's a really funky thought. We've now seen 10 of these binary black hole coalescences, various different masses. That's what this slide is showing. We've seen just one of these neutron star coalescences, and we've published papers about all of these things. The point is, this is an ongoing process, and in fact, the detectors have now reached the point where we think we're seeing binary black hole in spirals of about 1 a week. So it's gone from being earth-shattering news that we've seen one to routine in the space of just a few years. So that's a success story. 10 published, but we've seen many more. In terms of what is coming next, well, I've already spoken about the 2 American detectors and the one in Italy. The Japanese are literally any day now about to start taking data with their detector that they've built inside a mountain, which basically makes it underground. It turns out that's very good for eliminating some of the noise. And there's going to be another detector in India. So the point is, we're going to soon have quite a large network of these, and that helps when you want to figure out, say, where in, what direction in the sky one of these things has come from. But the only things that we've seen so far are 2 binary stars inspiraling and colliding. I said before, we might see exploding stars, we might see spinning stars, we might see something left over from the Big Bang. We'd love to see these things, so there's still a lot more that we've not seen. And it's certainly been in the case that whenever we've looked at the world in a new way before, we've seen something surprising. So I very much hope we'll see something that we didn't expect to at all. So I think I'll leave it there. Thank you.
Professor Ian Jones, thank you very much. That was a fascinating insight to some really new research work going on. Did it ever occur to you that you'd see these things happening so often, that they were potentially detectable?
The issue is that as your detector gets better and better, you can see a larger volume of the universe. And if you can see twice, if you can see twice as far, you see 8 times as much of the universe, because the way the volume of the sphere scales with radius. So that's why it's happened so quickly. You just make your detectors twice as good, and suddenly you're seeing things 8 times as often.
Fantastic. Anyhow, we're about to take a short break before you can ask Ian your questions. But the questions have you. Regular attenders will be pleased to know that after a lengthy negotiation with Hampshire County Council and filling out an extensive risk assessment, I am now authorised to set fire to anybody who goes there. Notwithstanding the fire alarm thing that we said at the start. With that caveat in mind, who would like to ask the first question?
What are the seismic considerations when you create and use one of the LIGO detectors? Because in particular, when you put the ones to come up, I noticed there's one in Japan, for example. I mean, how do you deal with seismic events?
Do I need a microphone?
Oh, sorry, I thought yours was back. Just had fresh battery in it now, so.
So the detectors are shaking around the whole time with seismic noise. Let me say a few things about that. You minimise it to the maximum extent you can, and the main way that you do that is through. So I said so these detectors are L-shaped, and you're bouncing laser beams up and down the arms. So they're bouncing off mirrors. What you do is you suspend the mirrors from not one pendulum, put one pendulum on another pendulum on another, so that even if the top of your column is shaking around quite a lot, because of this chain of pendula, the bottom one doesn't shake around quite so much. So that's one trick you use. What the Japanese are doing are two further things to try and reduce seismic noise. They're cooling their apparatus, and they're the only people that's done that, because that reduces the amount of thermal noise. And also, for reasons that aren't that obvious, seismic noise is better if you go somewhat underground. Now, technically, they're not going quite underground, they're going into the side of a mountain, but it's a similar idea. So all of those things reduce your seismic noise. It is always there at some level. So you've then still got the ability, though, to look at the outputs of two geographically widely separated detectors. And for the sorts of frequencies we're looking at, we don't expect there to be a correlation in the seismic noise. So really, that's then your sort of main remaining tool for convincing yourself that these signals are real. There's always some small chance that seismic noise could conspire to mimic a real signal, but it just becomes unlikely if you demand your signal should be sufficiently strong.
Next question.
You did mention about the gravitational difference between gravity and light reaction. But often what happens if the sun disappears, you notice the light from Earth with the gravity.
Right. Could everyone hear that? Or do I need to?
No.
Yeah. So the question was, if I understood it, what's the connection, say, if the sun was suddenly to disappear, would we see its light disappear, or would we feel its gravitational effects disappear? So the first approximation, what Einstein is saying is basically those two things would happen at one and the same time, because this changing gravitational field, can you hear me?
Yeah, yours is fine.
Yes. There are different channels. All right. The two things would occur because the gravitational change is occurring at the same speed as the light change. So it would be one and the same.
Okay. You sure?
I'm not sure if this is going either. It is a little bit. Right, okay. I'll speak up anyway. Some of the farthest things we can see in the universe, we can see because of gravitational lenses with which bends light to magnify the images. Do you get the same effect with gravitational waves? Are gravitational waves gravitationally lensed in the same way?
Yes, the answer is yes. We think that basically the way in which light propagates, we think, is exactly the same as the way in which gravitational waves propagate. So in principle, they're lensed. And in significant lensing, you need something of a coincidence in that you need a large mass almost directly on the line of sight. So we don't think that the 10 or so events that we've analysed so far were significantly affected by lensing, but actually one or two people outside the light collaboration have questioned that and suggested that maybe these were lensed and we've got the parameters slightly wrong as a consequence. I think the consensus is that probably hasn't happened, but sooner or later it almost certainly will do. Basically the answer is yes, that could happen, and you're right that lensing can make things stronger. So in principle we might get lucky and see something that's even further away than we would otherwise have been able to see because it was lensed.
Great, thank you.
I think the library have been buying cheap batteries again and struggling at the moment. So we can ask the next question. You get a slight dispensation. You can ask a slightly longer question.
The three solar masses that were put into gravity waves, is that roughly what you expected? It wasn't what you expected. Do they have any idea what it should be?
Can you hear me? Can you hear me? Yeah. So basically the answer is yes. But to the extent that, as far as we could tell, the signal really was completely consistent in all its details with the predictions of Einstein's theory of relativity. So both the shape, the frequency, and it's from the shape and the exact shape that we expected that number of three solar masses. Yeah, so
we did talk about testing relativity, with that signal, and yet it really did pass that test, and it's consistent that those 3 solar masses would have been emitted.
We've got one in this corner, so I don't have to go too far. Hopefully Jeremy will have the other microphone sorted.
Hold it nice and close in.
I understand that pulsars keep an incredibly accurate time. I believe there is some experimentation going on to detect gravitational waves by a disturbance of their time. Has anyone gone anywhere with that?
All right.
Can you hear me? Can you hear me now?
Yeah.
All right. So you're quite right. So pulsars are spinning neutron stars, and basically they're sort of lighthouses that nature has kind of provided in the universe, and they're incredibly good clocks, as you said. And so the idea is that if a strong gravitational wave was to propagate or pass through a pulsar or the Earth, that would have some small effect on the timing as received at Earth from the pulsar. So people are taking this idea very seriously. The idea is, by looking at many pulsars and the relative rates at which they're ticking, you form what's called a pulsar timing array. So you don't do it just with one pulsar. You basically see, oh, that pulsar's ticking a bit faster than normal and that one's a bit slower. That would be the signature of the gravitational wave. And a lot of people are working very hard on that. And it could have happened that they might have seen gravitational waves before we did with our experiments. They haven't seen anything yet. They're still hopeful. But what they really need is to find some more really good, stable pulsars to do it. Let me add one thing. What they would detect would be very, very low frequency gravitational waves, like in the nanohertz, so that's 10 to the minus 9 hertz. So they're sensitive to much lower frequencies than the hundreds of hertz that LIGO is sensitive to. So they would be detecting things like, well, they really could have a shot at seeing gravitational waves from the early universe, or whereas LIGO can detect 2 black holes colliding at masses, tens of solar masses, they would see signals from black holes with like 1 billion or 100 million solar masses. So they would be sensitive to somewhat different sources as compared with the Earth-based detectors.
I'd like to ask you a question about the way you were able to identify the masses involved in the collision. Because you didn't actually know how far the collision was away, which I would have thought was a prerequisite to working out what masses were involved, because I presume the inverse square law applies, and you need to know the distance before you work out the masses.
Yes, so that's a good question. So it turns out that you can do something rather surprising and rather magical with gravitational waves, which is, so let me back up and give some context for everyone. So one of the big problems in astronomy is that it's very difficult to measure distances. So suppose you see a star explode. You can't tell, is it a relatively nearby star exploding and producing just a bit of light, or is it a really, really distant star exploding and producing a huge amount of light? Because, because of this inverse law, more distant things seem fainter. That is a huge problem in astronomy. In gravitational waves, something really nice happens, which is, we don't just see how strong the signal is. And in gravitational waves, if a source is 10 times further away, its signal is 10 times weaker. It's a 1 over, it's not an inverse square law, it's an inverse law. But we've not just got the strength of the signal, we've got its exact shape and the way in which the frequency evolves in time. And this sort of breaks this degeneracy and means that we really can tell the difference between, say, 2 nearby, rather low mass black holes that would produce a weak signal, and 2 much further away, more massive black holes, because the more massive black holes would produce a different evolution of frequency in time. And so we say that gravitational waves, we don't quite call them standard counters, we call them standard sirens, because the frequencies are more like audible frequencies, but basically self-calibrating just from the gravitational waves, even for these black holes, we can figure out the distance to the source just from the gravitational waves alone. So we can do something that you can't normally do in electromagnetic astronomy.
Yeah, thank you.
Hopefully we're now back to a binary system on the microphones. So I'll go and ask somebody who's a bit further away now.
If I remember correctly, isn't there supposed to be some,
Close as you can.
some future space thing where they do the equivalent of LIGO between satellites?
Yes, that's right. I didn't talk about that. So it's called the LISA mission. It stands for Laser Interferometer Space Antenna. Basically, you can play this game with satellites in space. So instead of having, it's still kind of like an L-shaped thing, but instead of having mirrors fixed on the Earth, you've got like a mirror, or what's effectively a mirror in your satellite. And what that buys you is that you can have something that's much, much bigger than 4 kilometers. So I say bigger is better, right? The LISA mission will be like, what are hundreds of billions of kilometers between the spacecraft. So the idea is to launch 3 spacecraft, put them in a heliocentric orbit, and do gravitational wave astronomy that way. And because it's bigger, it's more naturally sensitive to lower frequency signals again. So again, it's more, this is what I said about pulsar timing arrays, it's more sensitive to signals from really massive black holes or the early universe. And that project got a big boost because that's sort of been delayed and delayed and delayed because it's expensive. But following the LIGO detection of gravitational waves, people really have now stuck their necks out, and it's scheduled for launch in something like the year 2034. So it's not tomorrow, but it's still, it's on a Korea time scale. You know, it could have been a lot longer.
We'll still be here waiting for the result. It's still just about working. Got somebody over here. Yeah.
Hello. Yeah. You said that you measured the expansion rate of the universe. How does that compare with other measurements that people have made with atomy? And briefly, you mentioned also that the radiation falls off as 1 over r, not 1 over r squared. Could you just say a few words around why that is?
Yeah, so let me address the second point first. So, yeah, with light, when we talk about how strong a light source is, we normally talk about how much energy we receive per unit of time, like joules per second per square meter. The natural thing to talk about with gravitational waves isn't the energy that we're receiving, but the amplitude, which is like this fractional, how much shaking around. But if you just, this is a bit technical now, but it's the answer. If you were to talk instead about the energy carried by gravitational waves, that would be an inverse square law. It's just, it's not the natural thing, because when we talk about how good our gravitational wave detectors are, it's much more convenient to say what fractional length change they're sensitive to. And then your second point about how our constraints on cosmology vary from other people's. So I've got a backup slide. In fact, if I can pointer again, there's actually a controversy. So there's this famous parameter called the Hubble parameter that astronomers are always trying to measure. And unfortunately, 2 different groups of astronomers, the Planck collaboration and the Schuss collaboration, have got different values. So this is a graph of their opinion as to what the actual value of this parameter is. It's got funny units. It's basically a measure of how rapidly the universe is expanding. And one group says it's about 68 in these units, and another group says that it's, I don't know, about 73 in these units. And they both got small error bars, so they really are completely disagreeing with one another. The LIGO result keeps everyone happy and sad at the same time. This is our probability distribution, and it's basically centered on the gap between the two with a huge error. We have an opinion about it, but it's not a constraining one. Now, in the fullness of time, we will improve. Now, they may improve and they may end up agreeing with one another anyway, but at the moment, we've simply got a result that is consistent with the two, but doesn't distinguish between them.
Very good.
At the beginning when you start talking about the... thank you. That when you put your arms, you create a gravitational wave. There is a mechanism that, depending on the mass and the frequency of movement connected with that wave, the same way when we detected here in Earth something to the power of minus 21, could you estimate also the original amplitude when it was created? Yeah, that's the question.
Yeah, so I think I understand it. So basically, the amplitude falls off in proportion to the distance. So if you go 10 times closer, the amplitude is 10 times bigger. But you can't really talk meaningfully about the amplitude of the gravitational wave at the source, because if you get too close to the source, and again this is slightly technical, if you get too close,
you don't see sort of a clean wave. You see a much more complicated bobbling around of the gravitational field, and it's only when you're sufficiently far away that you've sort of got a clean wave whose time variation is like a sine wave, and you can recognise as a wave. So basically, if you were to move your detector closer and closer and made it really close, say, to the pair of black holes, you'd go inside the wave zone, as we call it, and you wouldn't cleanly, you see a much more complicated time variation in the gravitational field, so you wouldn't cleanly call it a wave anymore.
This microphone seems to be very sensitive to gravitational waves. If you wave your arms around while you're holding the microphone, it seems to affect the volume.
Can you say a bit more about the mechanism for creating gravitational waves in the Big Bang?
Oh,
What do you expect?
So I can't say an awful lot about that, to be honest. So people do calculations as to how strong they are. But basically, the distribution of matter wasn't perfectly uniform and homogeneous early on. There was sort of density perturbation. So matter was, in a sense, moving around, and that produced the gravitational waves. People also think that there could have been peculiar things, like cosmic springs in the early universe that could combine and snap and twang and produce gravitational waves. So those are both mechanisms, but I couldn't be much more precise as to... I don't think I could easily say an awful lot more about the precise mechanism than that, really.
Would it involve sort of the ejection of dark matter when that sort of comes out?
Right. So the question is, so we think that a lot of the universe isn't normal matter that we see, but dark matter. So dark matter, we think, produces gravity just like normal matter. So if dark matter is moving around in some way, that will produce gravitational waves. One of the things we might cast light upon, if you pardon the expression, is what the nature of dark matter is with gravitational waves, but we've not seen anything yet that has any bearing on that.
Yeah, another question.
Just about neutrinos. Neutrinos are funny because they seem to oscillate, so that one would think they're travelling slower than light, but at the same time, when they have been observed, I think in the Kamiokande experiment, which somebody talked about here a couple of months ago, it appears that neutrino flux arrived before all the electromagnetic stuff. Now, how do they fit in? Have they been synchronized with gravitational waves?
So we have collaborated with people that run neutrino detectors to look to see if there were sudden bursts of neutrinos. Well, we think only just after the gravitational wave signal, and nothing has been found, which is not a surprise because almost of the 11 things that we've seen, 10 were binary black hole collisions, and we wouldn't expect neutrinos. But with the binary neutron star one, you would expect some neutrino production. We didn't see anything, but we didn't necessarily expect to because it would have been too weak. Now, with neutrinos, the theory is that they should go slower than the speed of light. So I'm not sure exactly what you're referring to where there was evidence for it going the other way around. I know that a few years ago, there was a big fuss that people thought it was going the other way around, but that claim has been retracted since because they found a flaw in the experiment. So my understanding is that we really do expect neutrinos to go somewhat slower than the speed of light. So we would expect the neutrino signals to arrive after the gravitational wave signals.
I think this particular event, which people study, occurred in the Large Magellanic Cloud, and, well, the distance is so enormous that one would think that if neutrinos were going to travel slower than light, they really would arrive afterwards. But I think the speaker who talked about it shows them what happened was the Kamiokande experiment found this burst of neutrinos, only about half a dozen, but quite significant. And then, after that, other telescopes turned towards the source and found pulses afterwards.
All right, I'm not familiar with that particular observation, but it does sound interesting.
Moving quickly on, we have another question. Yes.
in your first example of the collision of the two black holes, 29 and 35, whatever they were, what form did the residual 3% of energy take? Was it wholly absorbed in the collision, or was it dissipated as some other form of gamma ray or anything?
So we think that 3 solar masses, that the energy equivalent of 3 solar masses, that really was carried in the gravitational waves. So the waves, the gravitational waves themselves carry energy, so all of that energy was in the waves.
Meaning that the gravitational waves took it in all directions
Yes.
from the collision.
Yeah, there is some directional dependence, but basically there wouldn't be any single direction where there wasn't any gravitational waves emitted. There's some angular profile, but
And ultimately would become imperceptible.
yes, it all spreads out against weak, but the total energy remains the same.
Thank you.
Okay, I think we've come to a natural conclusion there. It's again a very informative and stimulating discussion, and please give a big thank you to Professor Ian Jones.